Okay, our third question from assignment 5 is child pulling a sled with a dog. This is a classic forces and motion question. So a child pulls a 15-kilogram sled containing a 5-kilogram dog along a straight path on a horizontal surface. He exerts a force of 55 newtons on the sled at an angle of 20 degrees above the horizontal. As shown, the coefficient of friction between the sled and the surface is 0.22. Part A says, draw a free body diagram. So we are going to keep drawing, even though you won't have to do it on a test. So we've got the weight of the dog and the sled pushing in this direction. We have some friction here. We have the applied force, which I usually use F sub A. You could say that's the tension. If you wanted to call that the tension in the wire, that's fine as well. And I have the normal force. That's my free body diagram. There are 4 forces acting on this dog-sled combination, and they are here. Now, I've made my normal force a little bit less than gravity because the applied force is helping the normal force. There is nothing in the rubric that said that, and unless they give you a grid to draw or to analyze, they probably don't care if you notice those subtle differences. So certainly these 4 forces here, 1 point for each force for a total of 4. They didn't mention this, but you probably get a point taken off if you have anything else labeled. So there's 4 points for that. Part B wants me to find the normal force. Okay, way back in Unit 2, we found the normal force by realizing that the net force in the y direction is 0, okay? The object is not accelerating up or down, so the forces up are equal to all of the forces down. Well, what's acting up? The normal force plus the applied force times sine theta equal mg. So what I have is my normal force is equal to mg minus Fa sine theta. Plugging in all the data gives us 181 newtons. I think I used 10 as acceleration due to gravity there. If you use 9.8, you get 177 newtons. Again, either way is fine as long as, even if they see a 10 or a 9.8 in there, they'll know that's what you're doing. So 4 points for this section, 1 point for realizing that the net force in the y direction was 0. 1 point for finding, it says 1 point for finding the weight, which I guess we found just by putting in there. So give yourself a point there. 1 point for Fn equals mg minus the y component of the tension, and then 1 point for the correct answer. Part C asks for the acceleration of the sled. Now the net force in the x direction is going to equal the mass times acceleration. The net force in the x direction is t times cosine theta minus the frictional force, right? Now the frictional force is mu k times the normal force, but remember our normal force here we calculated in the previous part. So I've got t cosine theta minus mu k times Fn equals ma. So we know t, we know theta, we know mu k. We calculated Fn in part B, so a little algebra gives you an acceleration of 0.59 meters per second squared to the right. Okay, part D, rubric. 1 point for the F equals ma statement. 1 point for realizing that the frictional force is equal to mu k times the normal force, and then 1 point for finding acceleration. All right, part D, how much work is done if the object is moved 7 meters horizontally? Okay, well, work is equal to Fd cosine theta. Okay, so the force he uses is 55 newtons. The distance it moves is 7 meters. And we can say cosine 20, and we get 362 joules. Now, what if you said, wait a second, I just want to use the x component of this force times d, and then I don't have to deal with the angle. That's totally fine, but the x component of this force is just FA cosine theta. So it's kind of potato, potato. It doesn't matter where you put in that cosine of theta, but it better be in there somewhere or we're going to get the wrong answer. So D is 362 joules. 1 point for the correct work equation, 1 point for the correct substitution there. Okay, and as FRQs tend to do, as soon as you feel like you know what they're doing, they do something stupid. And well, that's what they're doing again here. They say, after a certain amount of time, the dog rolls off the sled. Okay, fine. But the child continues to pull with the same force. On the axes below, sketch a graph of speed versus time for the sled. Include both the sled's travel with and without the dog on the sled. Clearly indicate with the symbol TR the time at which the dog rolls off. All right, so this is my graph for part E. I apologize for not doing it with you, but I had to make it work. So here we have the velocity of the sled. We know that when the dog rolls off, the velocity is going to increase because by F equals ma. Oops, sorry, I'm still on the line drawing tool. F equals ma. The child is still exerting the same force. When the mass of this goes down, the velocity is going to go up. The acceleration is going to increase. So we know there's going to be an increase. And we also know that the applied force is going to stay the same. So we don't have changing velocities except for at that 1 point. Now I went ahead and calculated the acceleration before, that was our last problem, is 0.59 meters per second squared. I went ahead and calculated the acceleration after the dog rolled off by recalculating the normal force, recalculating the frictional force, and refinding the acceleration, and I got 1.5 meters per second squared. Now, I know they don't ask to do this quantitatively, but I wanted to sort of get an idea of whether the, how much is the acceleration changing? Is it changing just a bit, like we wouldn't even notice, or is it changing a lot? And to be honest with you, the sled is 15 kilograms, the dog is 5 kilograms. That's a pretty significant portion, but still I'm not, and most of you probably are not that confident just assuming how much it's going to change. So I just wanted to know. So it about triples, right? So here's my straight line, straight line velocity versus time, which means constant acceleration. Then right here at TR, the time that it rolls off the sled, that's my second portion here. So the points for this were 1 point for indicating that the slope is going to increase at T equals TR. And then you get another point if the change is abrupt. So that is a very, it's not very, it's open to interpretation whether it was abrupt or not. So if you made an obvious change there at TR, you can have those points. So 2 points for that crazy extra part E.